Hey everybody, Dr. Retzik here with you. This is our first video in Chapter 16. Chapter 16 is meant to be an analog to Calc 3, but for functions of several variables. In particular, the parts of Calc 3 concerning parametric curves we will now try to ramp up into higher dimensions. Let's get started. Okay, so 16.1 is about something called line integrals. And it surrounds this picture. So you got a curve in 3D space, say like this. And it's got some starting point, and it's got some ending point, and it's traced out in a certain direction. And maybe the axes look like this. So this is happening in 3D space. It's like a corkscrew roller coaster, interesting curve in 3 dimensions. So that's the picture. And this curve C, you can call it C for curve if you like. C has a parameterization. There's a description of C in terms of the parameter t. So let's say that this curve is parametrized like this. The vector parametrization of the curve is at any time t, you have a certain x location, a certain y location, and a certain z location. And maybe t runs from t equals a to t equals b. So this curve is traced out in 3-dimensional space in that way. Now, the curve that we've drawn here, it looks nice, like nice and smooth. It's got like tangent lines at every point. There's nothing weird about it, no kinks, sharp corners, nothing like that. We're going to insist actually, for the purposes of this discussion, that the curve is actually smooth in the mathematical sense. So remember, smooth means this. Curve C is smooth. Meaning the derivative of the parametric description of the curve is never 0. Okay, so this is our standing assumption for the purposes of this discussion. And now we want to see what this has to do with Calc 4. Because so far, this is a purely Calc 3 parametric curves, Chapter 13 kind of thing. Okay. Let's consider a function. Let's say f of x, y, z. So this is a function of 3 variables, meaning the domain of this function is already 3D space. So you plug in locations in the x, y, z coordinate system to this function, and it spits out numbers. Now, the graph of this function is not present anywhere on this picture. In fact, we would need a 4th dimension, like if you wanted to graph w equals f of x, y, z. That's a 4-dimensional space in which the full graph of this thing f would reside. So we don't see f's graph on this picture. We could, though, think about what f does to points x, y, z from the curve C. So we're interested in evaluating f at the points along that curve. If we evaluate f at the points along that curve, there's a notion of f's integral along that curve. And the notion of f's integral along that curve goes like this. So you take the curve, which is curvy, and you divide it into a bunch of pieces. This should sound familiar from Calc 3. So now on each of these pieces, the curve is curvy, but maybe less curvy, one piece at a time, than it is curvy in an overall sense. and it looks like maybe I put in like 20 pieces. If you subdivide that curve into 20 million little sections, then any single little section is going to look almost like a straight line. Okay, now, back in the day, we used to call that little length of curve ds. So ds stands for this little tiny differential length of curve. And you can approximate the curve on that segment by a straight line, which ends up just being a hypotenuse of some triangle. And we know from Calc 3 that that ds is pretty much root dx squared plus dy squared plus dz squared. That's pretty much ds. Pythagorean theorem in 3D space. So the sense in which we're going to integrate this function along this curve is we're going to use each of those little segments, like say this one here, this one red segment here, we're going to use as the, quote, base of a rectangle, where the height of the rectangle is given by the function at that point on the curve. So you can try and think of it as a bunch of rectangles assimilated with their bases along that curve, but it's just a little weird because in what direction should that rectangle point? I mean, I guess in the w direction, where w equals f of x, y, z. But at least analytically, we have this way of writing down the integral. So here's a definition. The line integral of f of x, y, z along smooth C given by r of t over the interval t from a to b is, okay, now at long last we get to say what it is. First, the notation, these are just pixels. You write an integral sign, and then you subscript it with the curve c. You write the function, f of x, y, z, like usual. And then this integral is being done with respect to length along the curve. So you put in that little length element there, ds. Those are all just pixels on a screen. That is the notation. This equal sign is the definition of what we mean by that notation. That means integral from a to b, f of, okay, everywhere you see an x, you put what it is in terms of t. Everywhere you see a y, you put what it is in terms of t. Everywhere you see a z, you put what it is in terms of t. And then you multiply by that tiny little bit of arc length. And that tiny little bit of arc length, just like Calc 3, is dx dt squared plus dy dt squared plus dz dt squared, all done with respect to t. So that's what it means to do the line integral along the curve C. Notice here that that ingredient is nothing other than the magnitude of the derivative of the vector parametrization of the curve. And so this whole piece right here is just speed times little increment of time, and that's why we use it to stand for little increment of length. Distance equals rate times time. So all that ingredient at the end is just a tiny little bit of length along the curve, and then you're using that as the base. You're using f at that point as the height. That's 1 base times height corresponding to 1 little rectangle. And then the integral adds them all up. And that's what we mean by the line integral. Okay, so that's it. I think we should do one example just to make sure we can do it in practice, and then you guys can try suggested problems and then come to class with questions. Here's an example. Okay, so let's say we have this space curve. It's cos 2t, sine 2t, and t. Over the interval, let's say 0 less than or equal to t, less than or equal to pi, say. Okay, our job is to compute the line integral over that curve of the function x plus 3y take away z squared, all done ds with respect to arc length. Okay, so let's get an image for this curve. First of all, you guys recognize this curve as x and y. They're caught in a circular dance of radius 1, and as x and y are dancing in that circle, z just goes up, up, up as t increases. So this thing is a helix spiraling upward vertically. So something like this, let's say. And let's say this spot here is t equals 0. So what is that? When t is 0, we're at 1, 0, 0. And then as t starts to grow, because it's 2t inside the argument right here on these trig functions, by the time t reaches pi, 2t reaches 2 pi. So x and y, which are cosine and sine of 2t respectively, they're done with one dance of that circle. So the part of the curve that is relevant to us is this chunk right here. I'm going to put it in, yeah, purple's good. Let's put it in purple. So we're interested in this part of the curve. So that passes behind right there, curls around, comes back to the front. And that terminal point on the curve corresponds to t equals pi. Okay, and if you want to see the axes, then I guess the axes are like this. So this thing is coiling up around the z-axis. And that purple bit is the bit we're doing the line integral over. Okay, well, now that we have it written out, let's just do our work. Okay, here we go. So the integral over that curve of x plus 3y minus z squared done with respect to arc length is, by this definition right here, we know what to do. So that segment is traced out as t varies from 0 to pi. Everywhere we see an x, we're going to put a cos 2t. Everywhere we see a y, we're going to put a sine 2t. Everywhere we see a z, we're going to put a t. There's going to be this big square root piece, and the whole thing's done with respect to t. Let's talk about the square root piece. Under there, you have dx dt squared plus dy dt squared plus dz dt squared. Let's figure this out. R prime of t is negative sine 2t, cos 2t, 1. So the ingredients that go in here are sine squared 2t plus cos squared 2t plus 1 squared. But sine squared plus cos squared, no! Hey, I did the derivative wrong. By chain rule, we need a 2 out in front of each of those. So we got a 4 and a 4 right there. Whew! Now, sine squared plus cos squared is 1. So those first two terms just make a 4. Plus 1 more is 5. So I think we got a root 5. 0 to pi cos 2t plus 3 sine 2t minus t squared, all done dt. And from here, this is just a regular old integral. Regular old integral from here out. So I'll let you guys finish the job there. That integral is not so hard. A couple points on this example. The stuff inside the radical was friendly on this one because that trig identity just made it all constant. It's conceivable for a different curve with a totally different derivative that stuff under the square root might have t's in it and might not even be friendly. Not to mention this stuff out in front, depending on the function f and the parameterization r, that could be gnarliness with t's in it. So it's conceivable that the integrals we have to do on specific problems are not that easy. This one turned out friendly. Finally, if you find yourself wanting to do a line integral over a curve that is not smooth, if you had something like this, and that was your curve C, starting here, ending here, traced out in that order, then I think what you want to do is break the integral over the whole curve into this piece over C1 plus the integral from here onward. So call that piece of the curve C2. C1 and C2 are smooth. Their link up isn't, but that's how we're going to handle it. If you want to integrate over the whole curve, just integrate over each piecewise smooth chunk of the curve. Okay, so 16.1 is pretty straightforward as long as you believe in the definition of the line integral over the curve. It's going to amount to just doing a bunch of integrals with t's in it, or whatever the parameter letter is. Okay, go practice. Come to class with questions. I'll see you next time.